Okay. So, let's see. Is homework one going to be graded before the exam? Is there a question for the TAs? Let's see. Homework one was due last. When was homework one due? Last Friday, maybe. I mean, there's going to be differences between the sections, but homework one should be graded by the time of the exam. Yeah, today's Wednesday. Yeah. It should be. It should be graded by the time of the exam. Avery, is it timed? Like once we open, we have to be done by time? No, you have that whole window to work on it. So whether you do it in the first, hour and a half that it's posted, or whether you do it in the last hour and a half, or whether you work on it for 5 minutes at a time over the weekend, it doesn't matter to me. So, no, there is no like strictly, like time sensitive component to it. It will be, you have that full time to work on it. Doesn't matter when you start. I'm just gonna post like a PDF to Elms, so it's not going to be like an Elms quiz or anything. So there's no mechanism by which I could even time it. So I'll just tell you when I post it. So I'll post it and I'll send an announcement saying your exam's up, and then you'll have till like Monday at midnight to do it. Okay. So that's how it is. Neither I nor your TAs will be, that helpful with exam questions, but we'll be happy to answer any questions, you have that are related, just not, not questions specifically about the exam. Okay. What do I want to do now? So, I want to discuss, briefly some applications of tangent and normal vector stuff that we did last time. So, for instance, say I have a curve in space. Okay, so here are my axes, and here's my curve in space. And let's say, so here's my curve C. Of course, this has some parameterization. I'm not even going to write in the parameterization. So at a point on C, of course, now if I give you the parameterization, you know how to compute, say, the tangent vector T at this point and the normal vector. Right, so these are both unit vectors, of course. That's how they're defined, right? So it always works out that they're unit vectors. So let's consider any other vector sitting here, okay, at this point. So let's consider any other vector sitting here. We'll call it B. Okay. And so I want to, for various reasons, I want to be able to describe B in terms of the tangent and normal vector. What is it that I'm actually doing here? Okay, so my goal is to resolve a vector B lying in the plane spanned by T and N into components So what do I mean when I say this? So first of all, the plane spanned by T and N, right? So assuming that T and N are non-zero vectors, then they are guaranteed to be orthogonal. They're guaranteed to be perpendicular to one another, and so they determine a plane. Okay, you don't have to worry about the terminology used here. T and N determine a plane. So if you have two vectors and they're in general position, or in this case even better, they're orthogonal, so they're guaranteed to not be parallel. So as long as they're non-zero vectors, those determine a plane. This plane is called the osculating plane. This is called the osculating plane for C at the point determined by this. So if C is determined by some parameterization R of T, and this is my point R of T here. Okay, This is the osculating plane for C at R of t. Okay. So osculating, this is not oscillating. Osculating comes from the Latin osculatus, meaning kiss. So this is the kissing plane. Okay, this is the kissing plane. The reason why it's called that, and we'll see in other examples, especially there's some really nice, if you look up like a wiki article on osculating plane, there's some nice animated little pictures showing like what this means. For instance, for like a circular helix, what the osculating plane is doing, and why it's called the kissing plane, because the idea is it kisses this curve in a certain way. And so this is a notion that's more general, and the picture gets better with more and more examples, as we'll see. So what is the idea here that what is it that we're working towards? The idea is that I am considering this curve as a trajectory. Okay, so consider it as a trajectory followed by some particle. And if that's the case, this vector valued function r of t, right, what is this thing? Well, it's a position vector, right? This r of t is a position vector. Okay. And so I'm thinking of this curve being a trajectory traced out by something, some object, some particle, whatever. Okay, and the idea is that this vector valued function, this parameterization of my curve, is actually given by, or is telling me the position of this particle at some time t, right? Okay, so then this osculating plane is the plane determined by t and n, and so resolving a vector b into components depending on these vectors means that I'm just writing it as what's called a linear combination of these vectors. So the idea is that there's some multiple of the tangent vector. Right? There's some multiple of the tangent vector. We can call that b sub t. Okay, so b sub t times my tangent vector. I've scaled my tangent vector enough, and I maybe need to scale my normal vector a little bit more. So there's some other scaled version of my normal vector. I'll call that b sub n times n, such that when I sum those two vectors, what I get is b. So the idea is b is equal to this coefficient b sub t times the tangent vector plus b sub n times the normal vector. Okay, and now our goal is to not just do this for any vector. This is just showing you the general picture. The goal is to do this for the acceleration vector. Okay, so we want to consider this for the velocity and acceleration vectors associated to a position vector given by r of t parameterizing a curve. Okay, so just quickly wrapping this up. The idea is that I have a trajectory of some particle through space following a curve. If I have a parameterization of that curve, then r of t, right, this parameterization gives me the position of my particle at any time t. This traces out a curve. Well, now that I know that it traces out a curve, I can use the fact that I know how to compute tangent normal vectors to find, we'll see how, to find the what's called the tangential and normal components to velocity and acceleration vectors. Okay, and so my r of t, right, is describing position. Okay, so what do you think is going to describe velocity? Well, exactly the thing that described velocity before, dr dt of t. This is my velocity vector, right? So r of t is my position vector at time t. Dr dt of t is my velocity vector. Of course, this is the same thing as r prime of t. This is the same thing. This is what we're defining to be v. Okay. I know my r's and v's look similar. All right, so this is v. Okay, this is my velocity vector. Okay. Well, of course, note that the velocity vector is this thing we're calling v, which is r prime of t, right? But what is r prime of t? Recall that my tangent vector is r prime of t over the length of r prime of t. Okay. Or another way of thinking about this, right, in terms of r prime of t, if I multiply both sides by this length, r prime of t is equal to the length of r prime of t times t. And so this is really the length of r prime of t times my tangent vector t. But v is r prime, so the length of r prime is really the length of v. Okay. But really, if I'm thinking about this, so first of all, the velocity vector is a scalar multiple of the tangent vector. Okay. What is this scalar that it's a scalar multiple of? Or that the tangent vector is a scalar multiple, or that the velocity vector is a scalar multiple of the tangent vector of. What is this? This is it's the length of the velocity vector. It's the speed. Okay. So another way of writing this, of course, is right. I can always do this. Okay. So the velocity vector can be written as the length of the velocity vector times the tangent vector plus 0 times the normal vector. Okay, so what do I get from this? Okay, so the tangential component of the velocity vector is the length of v, i.e. the speed. Okay. While the normal component of the velocity vector is 0. Okay. So I want to do the same thing for the acceleration vector. Well, what's the acceleration vector? Well, it's just the derivative of the velocity vector, right? So I want to do the same thing for the acceleration vector. What's the acceleration vector? So it is defined to be dv dt. Okay. All right. Oh, I'm a little bit off the screen. Okay. So, A is dv dt, which is, of course, thinking of this as d dt of, recall we wrote this as the length of v times the tangent vector. Both of these things depend on t, typically. Right? And so I use the product rule here. So this is d dt times the length, or sorry, d dt of the length of v times t plus the length of v times d dt of t. So this is dt. Here I'm going to use that same trick. Recall that the normal vector n of t is t prime of t over the length of t prime of t. So another way of writing this is that t prime, which of course is dt, is equal to the length of t prime t times n. So rewriting this, this is ddt of the length of v times t plus the length of v times dt, which we've seen is the length of dt times n. And so we've done it. Okay, it's just in a slightly annoying form. Right, so the tangential component of acceleration is, we'll call that a sub t, and that is defined to be this coefficient on t. So this is the derivative of the speed, right? And the normal component of acceleration is what we'll call a sub n, and this is defined to be this quantity. Right, so the length of v, that is the speed, times the length of dt. Okay. All right. So we've computed the tangential and normal components of acceleration, which is exactly what we wanted to do. We can write this in a form that you might find slightly more preferable. So the way that we can think about this, so we can actually use the fact that t and n are orthogonal to write this in a form, like I said, that you might find better. So note, since t and n are perpendicular, we can write the following. If I consider the length of the acceleration vector squared, I know that that's actually just the acceleration vector dotted with itself, which, if we write this out, is the tangential component times t plus normal component times n dotted with itself. Now, we're doing this to take advantage of the fact that these mixed terms are going to cancel, because dotting t and n is going to give 0. So this dotted with this gives 0, this dotted with this gives 0, and so we're only going to get the pure terms. Okay, and so what this means is that I get ATT dotted with ATT, so that is A sub t squared. T dotted with itself is the length of t squared. Okay, plus same thing here, A sub n squared times the length of n squared. But what do you know about the length of the tangent normal vectors? The way that we've defined them, they're both unit vectors, so these are both 1. So actually, this is the tangent component squared plus the normal component squared. So actually, if you know the tangential component, which is easier to compute, right, bringing those formulas back real quick. So if you know A sub t, rather than computing this, another way that you could compute this is the following. You can actually solve for a sub n here. So a sub n is going to be the square root of the length of a squared minus the tangential component of acceleration squared. So this is another way that you could compute this normal component here. Okay, so let's do a quick example here of using this, and then I'll move on. So, quick example, let's let our position vector valued function be t squared I plus tj plus t squared k. Okay, find the tangential and normal components of acceleration. Okay, so I want to compute v, right? V is, of course, dr dt. So what is this vector v? So just computing this thing, I get 2t I plus 1j plus 2t k, right? Okay, that's easy enough. So now I can compute the length of v. Okay, so length of v is square root of 2t squared plus 1 squared plus 2t squared. So each of the 2t squareds gives me 4t squared plus 1. This is the square root of 8t squared plus 1. So that's my length of v. Okay, that's my speed. Okay, note that the speed depends on t. That's, of course, perfectly normal, right? This length of v is the length of r prime that we were computing when we were computing the denominator of the tangent vector, right? So this is perfectly normal. Okay, so then to compute the tangential and normal components of acceleration, what do I need to do? Well, to compute the tangential component, I need to take the derivative of this thing, right, with respect to t. Then to compute the normal component, I can take this thing and multiply it by the derivative of dt, but I could also use this shortcut that I have here. So let's continue on here. So a sub t is the derivative of the speed. So this is my tangential component. So what is the derivative of this thing, right? Maybe it helps to write this as a power, right? 8t squared plus 1 to the 1/2. That's what I'm differentiating. So remember power rule and chain rule. So this is 1/2 times 8t squared plus 1 to the minus 1/2 times the derivative of what's inside, which is 2 times 8t, so that's 16t. Okay, so this is 8t divided by the square root of 8t squared plus 1. Okay, so that's my tangential component of acceleration. Okay. Now, what is my acceleration vector? So my acceleration vector is dv dt, right? So this is bringing, so v is slightly off screen here, bringing v back, taking the derivative of this thing. So I get 2i plus 0j plus 2k. All right, so then the length of my acceleration vector is square root of 2 squared plus 2 squared. So that's square root of 8. Or if you really care, this is 2 root 2. Okay. And so what is my normal component of acceleration? Using this fact, here, my normal component of acceleration is the square root of the length of a, so that's 2 root 2 squared minus the tangential component squared, which I found to be 8t over root 8t squared plus 1. So this is 8t over root 8t squared plus 1 squared. So that's it. Okay. Okay, and this could be simplified slightly, but it's okay if you leave it like this. All right, because we're not doing anything else with it. Okay, so, oh, I'm slightly off screen there. I got pushed down by the paper. So as I was saying, this, this can be simplified to be a little bit nicer, but since we're not computing further with this, you don't have to worry about it. The only time that I would say that, you should absolutely definitely simplify as much as possible is when you're going to do further computations with it. Okay, so alternative forms. Here's some alternative forms that can sometimes be easier to remember or quicker to use. So these are exactly the same. I'll leave it to you to figure out why these are exactly the same. The tangential component acceleration can be computed as dotting velocity and acceleration and dividing by the speed. And the normal component is crossing the velocity and acceleration and dividing by the speed. Okay, so it helps you to remember these are alternative forms. You can deduce this just directly from those exact same formulas. Okay, so if there's any questions about that, you can put it in the chat. I'm going to continue on with some terminology here. So, as we saw, the osculating plane is this plane determined by t and n, right? The tangent and normal vectors. Okay, and of course, in general, because these vectors vary as you traverse the curve, this plane varies. It's not always the same plane. Okay. Now, if we wanted to try to describe this plane, well, we have a point on the curve. What do we need? We have two vectors that lie in the plane. They're actually the vectors we use to determine the plane. So how can we describe this plane nicely? Right? Go back to us writing the equations for planes. How do we do that? We needed a point, and we needed a vector that's normal to the plane. Right? Well, a vector that is normal to a plane containing these vectors t and n, of course, this works. Right? Crossing t and n. This has a special name. Okay? This is called the binormal vector. Okay. So T, N, and B are called a Frenet-Serre frame. For the curve C. And they satisfy what are called the Frenet-Serre equations, which I can't define yet, but I will by the end of class next time. The Frenet-Serre equations are the Frenet-Serre formulas. Okay, these are really, really, really nice. So if you look up Frenet-Serre frame, Frenet-Serre equations on Wikipedia, there is again a really, really nice animation showing exactly what this is. So in fact, look it up on Wiki. Look it up on Wikipedia. Maybe next time I'll share my screen and show it during lecture. But anyway, this is there's a really nice picture here of these things. Okay. Of course, we can actually compute the binormal vector in terms of velocity and acceleration as well. Of course, if you have the tangent normal vector in front of you, then just crossing them is the easiest thing to do. But another way to describe the binormal vector is it is v cross a over the length of v cross a. Okay. All right. So this thing is also a unit vector. You don't just know it from this formula, but it's a unit vector from this formula because both t and n are also unit vectors. Okay. Okay. All right. So let's see. No questions in chat. Cool. So now we begin to start some real fun stuff in terms of the examples that I can show you. So we have our last chapter 12 thing that we're going to talk about, and this is curvature of a curve. Okay. Now you might have, early on when you're thinking about curves, you might have thought to, inherently try to come up with a way of measuring how curved a curve is, right? So, you would want to be able to distinguish a curve like this from a curve like this, right? Okay. Or maybe even a curve like this. Okay. So the idea is, how curved is a curve, and how do I measure that? So the answer is the curvature. Okay, so let C be a smooth curve with smooth parameterization R of t. Okay. Then the curvature of C at a point R of t is defined to be kappa of t, which is the length of the tangent vector t, the derivative of the tangent vector. So it's the length of t prime of t divided by the length of r prime of t. Okay. So now you see my insistence that this is something that we talk about, because if you've computed the tangent normal vector, then you've already computed all the info you need to compute the curvature. All right, maybe I'll even note that specifically here. So note, if you've computed t of t and n of t, then you already have enough info to compute the curvature. Okay. All right. So, classical example, literally the first thing that we want to do is compute the curvature of a circle, right? Maybe you might say, I want to compute the curvature of a line in space. We can do that. We'll do that in a second. But first, let's compute the curvature of a circle. Okay. So, let's take, so let's see, be a circle of radius r. Let's be a circle of radius. We'll make it capital R so it's easier to differentiate. So let's see, be a circle of radius capital R centered at the origin in the xy plane. And so we already know a nice parameterization for this. So this is big R cosine t I plus big R sine t j, right? And t is 0 to 2 pi. Okay, there's our curve. Okay, so quickly, since we've actually already computed all these things before, what is r prime of t? This is minus r sine t I plus r cosine t j. Okay, the length of r prime of t is going to be r, but we'll compute it anyway. So this is square root of, so this is r squared sine squared t plus r squared cosine squared t. So clearly r. So that t is r prime divided by the length of r prime. So this is minus sine t I plus cosine t j. So that t prime is minus cosine t I minus sine t j, and that the length of t prime of t is square root of minus cosine t squared is cosine squared t plus minus sine t squared is sine squared t. So this is 1. Okay, so length of r prime of t is r. Length of t prime of t is 1. So my curvature, kappa of t, is length of t prime of t over length of r prime of t, which is 1 over r. So it's constant, but of course circles of different radii have different curvature. Okay. Note this is exactly intuitively what you understand about a circle, right? Note, as r goes to infinity, kappa of t for the circle goes to 0. Does that make sense? Does it make sense that circles of bigger and bigger radii have curvature that is smaller and smaller, going to 0 as the radius gets huge? The answer is yes, right? It makes sense. Why does that make sense? Specify a unit, right? Specify a plane that has an x, y axis. You're counting up by some units, right? So the x and y axes are both in terms of whatever units you've decided. And then once you've decided on the units, draw a circle of radius r. Then draw a huge circle of some gigantic radius r. Okay, and then think about going all the way out to your circle of gigantic radius r, and then looking at a little piece of it, right? What would that little piece of that circle be? Well, it would look like it was a line. In fact, if I hid the entire circle from you and just showed you a little piece of some circle of really massively huge radius, and I asked you, like, what type of shape is this, or, you know, what type of curve is this, you would tell me it's a line because it would look indistinguishable from a line. And if it didn't, I'd just make my radius bigger, right? And I would just keep making my radius bigger and bigger and bigger until it did look almost identical to a line. Okay, and so that would basically be, that is describing what's going on here intuitively with this curvature. Now, what is it that curvature is measuring? Unfortunately, for me to actually give you the full proof of this, it would require many lectures going off to the side, showing you what it is that's actually happening here. So I can't do that. But I can tell you what the answer is. What is the curvature measuring? The answer is the rate of turning of the tangent vector. So this is what curvature is measuring. And when you think for a second, right, oh, if I have curve and if my finger's tracking the tangent vector, then trying to come up with an intuitive description of how curved my curve is absolutely going to involve the rate of turning, right? Because if my tangent vector is turning, my turning is measured by something called a turning angle. So if my rate of turning is gradual, that is going to be a curve that is less curved overall than a curve that rapidly turns. Now, of course, you could have a curve that rapidly turns in some places and is a line in others, right? So in that case, near the points of rapid turning, the curvature is high, whereas, at the places where it's more gradual, the curvature would be closer to zero. Note also that by our definition, since the curvature is defined as a length divided by a length, okay, what's the thing here to note? This is always positive. Right, so kappa of t is, well, I shouldn't say always positive, it's non-negative, right? The least it can be is 0. Now, it turns out that there is a very useful notion called signed curvature that is a curvature such that it turns out that the sign curvature, if you take its absolute value, you get the curvature. Okay, so you can think of the signed curvature as a curvature that is allowed to be negative, and a lot of the statements that I'm going to make for the rest of this class about curvature, I'm actually going to be referring to signed curvature, but I don't want to make that distinction because it just makes things more confusing, and it flows nicer if I'm just saying curvature here. Although technically, like I said, for a lot of these statements, I have to say signed curvature. Okay, and so curvature is measuring the rate of turning of the tangent vector. And yeah, someone's saying out here disproving flat earthers. Well, that's exactly the problem, right? Is like, the Earth is big enough that locally it looks kind of sort of flat, right? I mean, if you look over horizon, right, you can see ship holes disappearing, right? So I mean, not entirely true locally, but still, it's big enough that locally it looks flat, right? If all of us were, on like a marble, the curvature would be a lot more apparent. So anyway, so when the radius is big, things look flatter or less curved. Now, for plane curves, and this is very important that this assumption be noted. For plane curves, the curvature determines the curve. What do I mean by that? I mean that if you know the curvature, then you know what curve it has to be. Okay, now what I mean by that is, for instance, we just saw that a circle of radius r has curvature 1 over r. You might say, well, what about some other curve that I find that has curvature, say 1/2, right? Say I find a curve in the plane, so this is only true for the plane. So if I talk about space curves, I can't say what I'm about to say. So in the plane, if I have a curve, and it has curvature 1 over 2, right, 1/2, then that curve must be a part of a circle of radius 2. Okay. So this is a very strong fact. This is really, really nice. It tells you that if you know the curvature, then basically you know the curve. Now, this isn't true for space curves. We need something else called the torsion that I'll talk about later. So it's not true for space curves, but it's true for the plane. But note, although this means that we can specify a curvature to nail down curve. What I mean by that is once you specify a curvature, there is basically one curve that has that curvature. Okay. So once you specify curvature 1/3, basically the only curve that has that curvature is a circle of radius 3 or pieces of it, right? Now that circle could sit here, it could sit over there. It could be the upper part of the circle, it could be just a tiny part of the circle, but the point is that basically that curve is nailed down what that curve has to be. So although this means we can specify curvature to nail down a curve, this doesn't always work out as nicely as you might think. So what do I mean by that? Here's an example. Suppose C is a curve for which kappa of t is equal to t. Now, really, I need to specify the sign curvature here, but again, don't think too hard about it. All right, so it's fine to do this. So the bigger thing is I just specify a curve C that has curvature just equal to t. Okay, you'd think this is like one of the simplest possible curvatures, right? So what curve C is this? Since I've said up here that curvature determines the curve, once I've specified that I have curvature that is equal to some function, then this should determine exactly the curve I get. What curve C is this? You might look at this and try to think in your head and say, oh, well, like it can't be that complicated of a curve. This curve C is Cornu's spiral. What does Cornu's spiral look like? Well, it looks like this. Okay. So that is the curve that has that curvature. This gamma of S here, this is from a book from Math 436. This is gamma of S is how they write R of t. So this is the parameterization of that curve. So its parameterization is that. These are called Fresnel integrals. Okay. So, and I'll write that here in a second. So here's what Cornu's spiral looks like. This is what the curve that has curvature just equal to t looks like. And like I said, the parameterization of that curve is this awful thing. These can't even be evaluated, right, normally. Okay. So those are called Fresnel integrals. So maybe I'll actually write that. So it turns out it's a curve that has the following parameterization. So R of t for this curve is the integral from 0 to t of cosine of u squared over 2 du I plus the integral from 0 to t sine of u squared over 2 du j. That's your this is your parameterization. Okay. These are integrals that can't even be evaluated in the normal way. Okay. All right. Let's see here. So the point where the tangent touches the line of the bigger circle moves faster, but the change in directions remain the same since they are parallel. Let's see. If you're talking about the Cornu spiral, I'll have to go back to it. You're talking about here. The idea is that, of course, as you're more tightly spiraling, okay, so just look at half of it, for instance. Don't worry about this bottom half for now. As you're more tightly spiraling, the curvature is increasing, right? And that makes sense because, of course, your curvature is just t. So as t is getting bigger, this curvature is getting larger and larger, right? Okay, so like I said, that is an example of a curve being determined by its curvature. But look how simple, right, this is, and it gives you a curve that's pretty complicated. So, I'll write a couple more things and then I'll be done. For space curves, curvature alone does not determine the curve. We need torsion. Now, what is torsion? So, let's define it and then we'll talk about it next time. So let me quickly define the torsion. Let's see, what's the most convenient? Most convenient explanation of the torsion is as follows. So definition of torsion of a curve. So let C be a smooth curve with non-zero curvature everywhere. You will see why this is required. Okay. So it's got to have non-zero curvature everywhere or we can't define the torsion. Okay. Then the torsion of C is tau of T, which is defined to be if C has parameterization R of T, this is defined to be R prime cross R double prime dotted with R triple prime divided by the length of R prime cross R double prime squared. Okay. All right, so that's the torsion. And I'll explain next time how the torsion, together with the curvature, determines a space curve. And then I'll take a bunch of random questions about the content from chapters 11 and 12 on Friday. So anyway, I think that's it for today. So you have homework due tomorrow night. On Friday, like I said, I'll take some questions from just general chapter 12 or chapter 11 and 12 stuff. So if you have any remaining questions, let me know. Then I'll post your exam on Friday afternoon. Okay. So we'll compute the torsion. We'll compute the torsion of a nice curve on Friday. Don't worry. So anyway, I think that's it. So I will see you all on Friday. Oh, hyperbolic functions in the homework. Okay. So, what are hyperbolic sine and cosine? So, we have sinh t and cosh t. So the way to remember these is that they match up with sine and cosine. So that sinh of 0 needs to be 0. So that's how to remember the way that this goes. So this is e to the t minus e to the minus t over 2. And this is e to the t plus e to the minus t over 2. Okay, so that's it. Quickly, you will understand that compute ddt of sinh t. What do you get? Oh, you get cosh. That's cool. And compute ddt of cosh t. You don't get minus sinh t, you actually just get sinh t. Oh, very nice. They're actually nicer than sine and cosine, right? Okay. Yeah. Yep, so there you go. So now that you know that they're just these exponential functions, you know everything you need to know about them. You can Google them if you want to see the graphs of these things and how they look. All right, but this is how it goes. All right. So yeah, if you just Google hyperbolic trig functions and their derivatives, you will see all. You will understand all things. So anyway, I will see you all on Friday.